All right, well, shortly we're expecting Jared to arrive, and he's hopefully buying chicken strips for everybody or something like that. I don't know. Anyway, he's out buying food. All right, so we're moving forward. How did people feel about the last problems? They're pretty neat. I mean, they weren't all that hard. Did you have a question about some of them? They were pretty cool, right? I mean, it's actually pretty neat how you can come up with these little linear approximations over little ranges to help solve problems, come up with these approximate solutions. It's pretty cool stuff. Today, I'm actually surprised they're taking a whole day to talk about this subject on, what are we on, 4.3?
Yeah.
Maxima and minima. Basically, they're just sort of formally defining some ideas that we've been using before and so on. And this is this idea that, you know, a function, let's say here's a nifty function here. You know, assuming it isn't a constant function, you know, or something like that, or just a line, it may have maxima and minima. Maxima and minima, but we're going to have some ways of like attaching some vocabulary words to this here. By the way, just because the book drops this term a couple of times here, whether it's a maximum or a minimum, the right word is it's an extremum. Or extremum. Extrema. By the way, so with the A on the end, that's the plural. You know, they are maxima. Or it is one, you know, it has one maximum. Okay? But anyway, so extrema just means it is maxima or minima. Okay? There are multiple of them. Now, like that function I have drawn up there, which looks something like, I don't know, x squared plus 1 or something like that. Heck, let's even write that down. This could very well be x squared plus 1 that I just drew up here. Well, I don't think we have any real trouble figuring out that this guy has a minimum. There's clearly some value here where it is a minimum. Mathematically defining that is a little bit fancy. I mean, what we mean is that there is some value here, like x equals c or something like that, at some value of x, like maybe x equals 0 in this case, where there is some range, we'll call that interval I, there's some range, and this is the lowest one in that range. Now that range might be really small. That doesn't matter. It might be really big. That range might be negative infinity to infinity, but in that range, this is the smallest one. Okay? Now, that range might be smaller, it might be bigger, but whatever. So as long as C is inside this range I, and we don't care, as long as that range is at the beginning, and x of C is smaller than any other x that was inside of that, f of x that was inside that I, then that's a minimum. Now, correctly speaking, this would be a relative minimum, because it is, you know, just in that little range right there. In other words, we could have had a function where, like, I don't know, maybe something like this happens. Okay, this is a relative minimum because there is some range right here, I, where this is the smallest value in that range. And again, that range might be pretty small. Okay? But it has a range around it. You can think of it as like if there was, I don't know, rain falling from above, it would collect in here. Okay? That makes it a relative minimum. This would be another relative minimum, and so on. On the other hand, this relative minimum right here is also an absolute minimum. Now your book, oh, I already got locked off. There it goes. Is a little bit goofy about this. Okay, I always heard this word absolute minimum as in, that means that it is the minimum on the range x equals negative infinity to infinity. Okay. That's not what your book says. Your book says it's the absolute minimum if they give you a range, like maybe negative infinity to infinity, but they give you some range and it is the minimum in that range. Doesn't mean that, like, relative minimum means there is some range around this that it would be the minimum. In an absolute case, they mean over the range we're telling you this is the lowest one. Alright, whatever. What we want you to notice here is, like in the case of this function that I'm drawing here, x squared plus 1, there is no maximum here. At least not on the range negative infinity to infinity, because the values just get bigger and bigger and bigger. There is no biggest one. But on the other hand, if we had said on the range negative 2 to 1, what was our biggest value? Well, it could be found. You can make a graph, you can do whatever you have to do to figure it out. In other words, there's just sort of some terminology here. Just sort of sorting out the relative minimum or the relative maximum means that it is the lowest or the highest in some range. You could make a range and it is the biggest in that little range. Right? It is that. Now, you know, on page 367, there's a whole bunch of examples of what we could mean by minima and maxima. But I want to show you something that freaked me out a little bit when I was looking at these. I had never thought about this, or at least certainly hadn't thought about it in a long, long time. But they have one of their examples that looks something like this. Here's some goofy function that has a graph that looks something like this. And then this is an open circle. And then here's the closed circle, and it goes something like this. I don't know which one is it, the fourth one or something on that examples there? Looks a little bit like that. And it wants to know what is the minimum. Now remember, let's use the word here correctly. The minimum is the value of x that produces this lowest value. Okay, now, because this is an open circle here, they're going to say that there is no minimum of this function. The idea being, there is no value of x that gets you to the lowest possible value of this function, because no matter what, you could get closer. I mean, let's say this open circle right here is at, I don't know, 2 comma negative 2. All right, well, but that isn't the value of the function. F of 2 is actually this thing. F of 1.99 is here, but F of 1.999 is here, and F of 1.999, you can't get close enough. Okay, that's pretty neat, but that's kind of a theory of limits thing. I wouldn't get just too bogged down about that. In general, when we want to ask about this stuff, we want to know how we're going to find these guys. Now, yep. Okay, that's what we said. I mean, if we had some graph like this, and it says find the extrema of this function. All right, so this is some graph of something here. Well, we already learned about this one time before. I'm actually kind of surprised, like I said, that they put a whole section about this. Because what you could do is just find the derivative of this function and find the place where the derivative is equal to 0. Because any place the derivative is equal to 0 is a place where it's horizontal, with the slope of the function horizontal. All right, that's easy enough. So we take the derivative of this function and, oh, I don't know, let's say this function is f of x equals x cubed plus 2x squared plus x plus 5. That could be, I don't know. I always have to play with it to see if that could be right. But it could be, something like that. Well, if we took the derivative of this, it would be something like that. And then we would have to factor, or whatever it would take, to set this thing equal to 0 and find the values of x that make this true. How are you going to do that? Factor maybe use quadratic equation, all right? But you're finding the values of x that make this true. And let's say you got, I don't know, x equals, just to make it look like this thing over here, -1 and x equals 2 or something like that. Okay, that's not right in this case. But you could use a quadratic equation, you could do factoring or whatever. So then x equals -1 has a maximum, a relative maximum, and at x equals 2, you have a relative minimum. And that's pretty slick. You might, though, find yourself slightly misled by that. Because what if your function did something like this? I don't know if I did draw this very well. Let me try this a little bit better. What if you had a function that does have a slope? There's sort of an inflection point right here, where the slope is 0. That's neither a maximum nor a minimum. What about a function that does something like this? You know, where it's put together piecewise like that. What's the derivative at this point?
Wouldn't it not be a function so you can find
It's undefined at that place, right? No matter what though, these things are all examples of critical points. There are definitely critical points, that's the vocabulary word they want you to know, where you're going to have to test. You're going to have to make yourself a graph or something like that and decide, hey, wait a minute. Either my derivative is equal to 0 here, or if my derivative is undefined, those are the places I'm going to have to check. I'm going to have to look on a graph or something like that and see what's going on. Later, we're going to see that there's other ways that we can figure out. See, here's the deal. What we just did here would have told us that x equals 1 is a critical point, some kind of extremum or something, and here's x equals 2. And we could have then used a graph from your graphing calculator, Desmos, whatever you want to do, to figure this out. Then are they maximum or minimum? Turns out you don't have to. It turns out there's going to be a way to tell, are they a maximum, a minimum, an inflection point, whatever. But we're not there yet. For now, if they say, what is it, a maximum or minimum or whatever, make a graph.
Couldn't you plug your zeros back, your zeros back into like the original function to figure out the y's and see it?
Yeah, well, I mean, isn't that basically what graphing is?
Yeah.
Yeah, I mean, basically, yes, you're right. You could do that too. But yeah, you're going to be just experimenting with it for today, because, I mean, there is a way we're going to use second derivatives and things like that later to figure out if these are maxima or minima and so on, but we're not ready to do that yet. Your book does jump in one last little time just to show you one thing that's another possibility. If your function is nicely behaved, like it's a continuous function, doesn't have all those crazy steps or jumps or corners or anything like that, if it is some kind of well-behaved thing, but it, you know, could be quite as busy as you want it to be, and you're supposed to find the absolute maximum or the absolute minimum of that function on that range. So there's some range. We're going from here to here. This is our interval I. And we're saying on that range, where's the maximum? There is a pretty nifty rule. Your absolute maximum and your absolute minimum will either be at one of these places where the derivative is equal to 0, or at the beginning or the end of the range. So your maximum, your absolute maximum, the highest place on the range, has to either be one of these places where the slope is equal to 0, or the beginning or the end. Like in this case, notice it turned out to be the end. The minimum had to be at the beginning, was at the beginning in this case. This is pretty neat, and I believe your book calls this Fermat's theorem, which I think is interesting considering there's only about 1 million things in math called Fermat's theorem. But whatever, it's what we're calling it this time. Alright, I'll help you with one of the problems on the way too, where you get a list of these places where you take this derivative and you set it equal to 0, and you get a list of the places in that range where you could have an absolute maximum. You're going to have to test it, but then you also have to test the beginning and the end of the range. I don't love this section. I think most of the things in this section we could have already done. I think, in fact, on the last test we did some of those. We found some maxima and stuff like that. We're leading towards a better set of tricks to start figuring out, without drawing a graph, which ones are the maxima and which ones are the minima, but we're not there yet. I guess they're just sort of reviewing this. Let me get you the list of problems for this. Hold on. And we will move from there. These are not so hard. Hold on. There it is, planning calculus. What page are we on here? I don't know. Could it be page 376? That sounds right.
We're definitely past 364. That's
Yep,
like
so
that.
376 is where we are. Page 376, you're just doing numbers 109 through 133 odd. And you're also doing problem 141. Alright, so this is I feel like you've got 45 minutes to be doing this one. You can probably get this one done in that much time. This is a relatively small assignment. It shouldn't take you too long to get this one done. Not all that much new material. Alright, I'm going to turn the camera off.